So we're going to start with the basics for a solution. A solution is made up of two parts, the solvent and the solute. All right, and so the way I usually like to just kind of draw this out is then a solution as a solvent and the solute. Now the solvent is what you have more of. You've got more of it. The solvent dissolves. The solute is dissolved. If I can spell dissolve, and so learning this language really kind of helps for this. When I was a young man, just starting to drink coffee, oh man, my dad likes strong coffee, and so I would always add a bunch of sugar to it, a bunch of things to it, and he would always tease me and say, "You want a little coffee with your sugar?" And he was actually right. If I'd added more sugar, then it becomes the solvent. All right, so I might ask some questions, simple as if I have 5 milliliters of acetone and 3 milliliters of water, what is the solvent? And so the solvent is just whichever one I have the most of. All right. So one thing that we want to be careful of here is that when we start mixing these, the volumes are not additive, and we'll see that happen over and over here where we add the grams or we do things with the volumes, but if you add two different liquids, you cannot predict what their volume will be because the spacings and their densities interact with each other, and so you can't just add up the volumes. All right. Now I also have on here that it says the aqueous solution, that the solvent is water. That's easy enough. But we can also have air, and it says the solution in nitrogen. And that's because 79% of air is nitrogen gas. And so you have all these other things that are in air, oxygen and water, carbon dioxide, carbon monoxide. And so they're all dissolved in the nitrogen because there's more of it. So the solvent would be N2. Okay, an alloy, which is just a mixture of metals. All right. Again, we've got our definitions for electrolytes and non-electrolytes. Not a problem. In lab, we run into students running trouble all the time between the difference between clear and colorless. So clear means you only see one state of matter. You don't see two different liquids where you can tell where one is and where the other one is. Oil and water, when they don't mix like that. Or if you have a solid floating in a liquid, then it would be cloudy. All right, so the opposite of clear is usually cloudy, and colorless is just lacking color. So you think solutions can be blue and clear, all right, or cloudy and yellow, those kind of things. So don't get them mixed up. Going up, how is solubility? In our term is light dissolves light. Now in solubility, we're now looking at this in slightly different terms than we did originally. Originally we looked at solubility and we're discussing it in terms of solubility was about how is something soluble or is it not? It's just a yes, no. Now we talk about how much. All right, and solubility causes us some interesting things. All right, so this idea that temperature increases solubility. I'm going to play with this idea on gas. We'll come back to in just a little bit, but I want to look at these definitions, saturated and supersaturated, and play with this idea of solubility. So if I take a beaker and I put some water in here, so here's my water, and I start adding some salt, some NaCl. Now, salt is soluble in water, so it dissolves and it dissociates and it spreads out. But what if I keep adding salt and keep adding salt and keep adding salt. Eventually, this solution gets as much as it can hold, and any extra comes out as a solid. So down here I have some NaCl that's a solid, and up here I have some NaCl that's aqueous. Aqueous, if I can make A. Try that all again. There we go. Aqueous. All right. So what's going on is actually more complicated than it seems. All right. What happens is you get local little places of higher temperature and little places where, as the water comes by, it grabs up and dissolves some of the sodium. It goes up into solution and splits up. But now I've got too much in solution, and it's got too much there, and so some of it has to come out. And so some's constantly going in, some's constantly going out. All right. So this is much like what we refer to as, this is called a dynamic equilibrium. Dynamic means we can change it. Equilibrium means the rate going in is equal to the rate going out. Now, rate is speed. All right. And so how fast things are going into solution is as fast as they are coming out. So if that's happening, the amount of salt here doesn't change, but the actual atoms that are involved are constantly being swapped at the surface. Some are going in and some are coming out, and they're constantly going back and forth. All right. Now it's dynamic. We can change this. If we increase the temperature, we increase the solubility of salt in water. All right, and this gives us great power. So I can raise the temperature, and more of this salt will go into solution than is coming out. And so we'll have less solid and more in solution. If I cool it down and lower the temperature, then I lower the solubility and it comes out faster, and I'll end up with more solid down here and less in solution. Easy enough. So this idea of equilibrium will hit you with this term a lot. Rate in equals rate out. What I usually like to think of is going to the store. All right, and so when I go to the store, I'll pick on Walmart. Everybody likes to pick on them. So I go to the store, and there's people in these checkout lines, and what they want, when you get there, you want to get out of the line right away. But you notice there might be 3 of these, and only one of them is open. And it drives you nuts every time, right? And so what they want is, as more people get in line, they get you out at that same speed. All right. And so if they have 4 people in line and a 5th one joins and they still haven't got it out, the line would get longer. So what do? They open up a second one so they can get them out faster. All right. Or what if, but they don't want everybody just zooming in and zooming out. They want you standing in line because you make a lot of purchases sitting there looking at the magazines. Ooh, I need a pack of gum, or hey, there's some playing cards, or they always have toys or candy there so that your kids will gripe and say, hey, Mama, I want that, I want that, I want that. All right, they want you buying all that and standing there for a little bit of time and not just immediately leaving. And so you'll notice that they can control how fast people go in and out by how many of these stations they open. And so if they ever close one, or I'm sorry, have them so many open where they're getting them out twice as fast as they get in, they'll get to where there's no line. And they'll immediately come and send this person on break so that they can slow everybody down and get the line to build back up. And that's how they can control how fast they get people out of the line, is by how many of these they have open. All right, and so it's a dynamic equilibrium. And it also comes into play what time of day. So if it's 5 p.m., everybody expects you're going to have to stand in line no matter where you go, and you might put up with a line of 5 or 6 people. You might grumble about it, but it's that way everywhere you go. And you go, oh man, why don't they open more? Well, they know that you're still going to continue shopping. They're still going to, so they make enough money by you buying that extra stuff and by the fact that they'll eventually get you out of there and they didn't have to open up and pay another employee to get you out faster. Okay. Now, if you go at 3 a.m., you might only be picking up a couple of things, and you don't expect to stand in line that's 5 people deep. You might just say, forget it, and walk out. All right. So they actually lose money if that line is too long at that time. So they control this by how many stations they have open, and so that's what they have different expectations at different times for that. So dynamic equilibrium. Now, we can play with this picture a little bit, and the key to it is temperature. So when I have as much dissolved as I can, it's saturated. So this solution would be saturated if I see any solid down here. So the solution is saturated. Now, when I want to play with this a little bit, I can make a temporary condition super, in other words, more than saturated. Alright, so super saturated is a temporary condition. And this is the same idea as we use to make Jello. Alright, it's the same process. A lot of times we use this as a recrystallization process. So here's the way you would do that. You would raise the temperature until it's hot enough to get everything dissolved. And once everything's dissolved, you slowly cool the temperature down. And if you cool it down gently enough, it'll stay in solution for a limited time. While it's in solution, that's a super saturated solution. And if you let it cool slowly, it'll come out one molecule at a time, and usually it'll come out in either nucleation point, either another crystal, or a scratch in the glass, or if you wanted to make rock candy, a piece of string, or a popsicle stick. Alright, so if I take some sugar and dissolve it into water, and get as much as I can into that boiling water, and then let it cool down real slowly, it'll come out as one big crystal. It'll come out one molecule at a time, and it'll just form these large crystals. If I cool it down real fast, it'll come back out as a powdered sugar again, and it won't be super pure. It just comes out all at once, and anything else that was in the water comes out at the same time. All right. So when you make Jello, that's actually the instructions for Jello. When I look at that, it says take the box and dissolve it in so much hot boiling water. And then once you've got it, stir it completely until it dissolves. Add some cool water. You're just cooling it off gently, slowly. Then you're gonna put it in the fridge and gently cool it and let it slowly come out. And it, instead of forming a solid, it forms a gel and traps the water in there. All right. If you've ever tried to make Jello and speed up the process, stick it in the freezer. Ooh, it's nasty. It ends up tasting and looking about like the bottom layer of your shoe. Just don't do it. Don't do it. All right. So this idea of dynamic equilibrium, the rate going in is the rate coming out. We'll also ask about saturated and super saturated. So people say, how can it be more than the max? Well, it's a temporary solution. It just happens for a small amount of time. All right.